In this section, we're going to expand our application of the working energy methods beyond the traditional Bernoulli equation. We're going to include the effects of heat and viscous fluid flow, along with work input from a pump and work output due to a turbine. We're going to restrict ourselves to incompressible flows. So this equation is what's known as the general energy equation for incompressible flow. And you can have some very similar characteristics to the equation we've looked at before. It's got a couple extra terms. H pump is the useful head delivered to a fluid by a pump. H turbine is the extracted head removed from the fluid by the turbine. And HL is the irreversible head loss between the input and output due to the piping system. So this is basically a friction kind of term. So our book spends a lot of time developing this equation, but honestly, it's best to see how this equation is actually applied in a couple of examples. Let's take a look at example 510. Here we have a turbine used in a small hydroelectric plant. If the discharge through the 0.3 meter diameter tube at B is 1.7 cubic meters per second, we want to calculate the power that's transferred from the water to the turbine blades. So here, as the water flows through, it's going to turn the turbine blades and create electricity. So this is a hydroelectric generator. We're told also that the frictional head loss in the penstock, which is the tube that runs down to the turbine, and the draft tube is 4 meters. So this is a steady flow. We're also told that gamma is 9810 newtons per cubic meter. So we're told the Q value, and we know what the area at B is. So we can, well, we know the diameter, so we can calculate the velocity. So Q is 1.7 cubic meters per second. The area is pi r squared, so we can calculate the velocity at B to be 24.05 meters per second. Now we can use the energy equation between A and B. So we can write down the generalized energy equation. And remember, we got these extra terms we have to take into consideration. So at A again, so this is the top of the reservoir. So the pressure at A is going to be the same as the pressure at B. Let's just make both of them 0. So the pressure at A is 0. The velocity at A, again, is 0 because it's at the surface level. And so it's going to be much less than down here. So let's just set the velocity at A to be 0. Looking at the diagram, the Z value at A, if we measure things from our reference level, which is the height at B, is measured to be 60 meters. So that's the Z of A. Head loss of the pump, we don't have a pump in here, so that this term is 0. The pressure at B, we found what that is, so we know what gamma is. The velocity at B is, we calculated that. We know what G is. ZB is at 0 because again we're at the back at the reference level. We don't know what the H of the turbine is. That's what we're trying to find. And H of L, remember, is the friction term that we were told is 4 meters. So the only thing we don't know is head loss of turbine, so we calculate what that is. It's 26.52 meters. Our book gives us an equation for power in a turbine. It's the Q value times gamma times the head loss. So Q is 1.7 cubic meters per second. Gamma, we're told. The head loss we just calculated. So we can calculate the power for 442 kilowatts. We can also calculate the energy loss due to friction. It's basically the same equation, except instead of using the H of the turbine, we use the head loss term, which is what we were told for was 4 meters. So that's 66.7 kilowatts. As our final example, let's take a look at the example 513. So here we have a pump, where we have an irrigation pump is used to supply water to a pond. So we're pumping from A, pumping up, dumping out the water to B. The rate at B, we're told, is 2 cubic feet per second. If the pipe is 6 inches in diameter, determine the required horsepower of the pump. Assume the frictional head loss per foot length of pipe is 0.1 feet per every foot. So draw the energy and hydraulic grade lines of the system. Assume gamma is 62.4 pounds per cubic feet. The first thing we can do, we can define our control volume. Since the pipe has a constant diameter, it's easy to calculate the velocity. It's going to be the same everywhere. So we're told what Q is. It's 2 cubic feet per second. We know what the area is because we know the diameter of the pipe. So we can calculate VB 10.186 feet per second. So now let's take a look at the energy equation. So we found the velocity at B. The pressure at B is going to be 0. So this first term is 0. ZB, we're told, is 8 feet. So that's the term here. We don't have a turbine, so that term is 0. And the head loss is, so the total distance, so here, to find the head loss is 0.1 feet per every foot. So I know this is kind of a strange unit. It looks like it cancels out. And again, it does, but it's best probably to leave it in there. So here we have to calculate the total running feet. So we start here. We got 7 foot of pipe and then 8 foot of pipe. So it's 15 feet total. So it's 0.1 foot loss per every foot. So we got 15 feet. Now on the left-hand side, the pressure is 0. The velocity again is 0 because it's right at the surface here. And H of pump, that's what we want to calculate. Z of A, we're at the reference level down here at the bottom, so that term's 0. So the only unknown is the head loss of the pump is 11.11 feet. So similar to the previous problem, we can calculate the power of the pump and the power loss due to friction. Both of those terms is this Q gamma times the appropriate head loss term that we've calculated both of those in each case. So finally, let's calculate the energy grade line and the hydraulic grade line. So at point B, we know what the velocity is, so it's very easy to calculate the velocity gradient there. It's v squared over 2g, 1.61 feet. And this velocity, again, this velocity remains constant because the pipe has the same diameter throughout the length. So now we're in a position to find the energy grade line and the hydraulic grade lines. To do that, let's use the generalized energy equation between points A and A prime. So there's no pumps or turbines, so those two terms are 0. They're at the same elevation, so the ZA prime and the ZA are all 0. The pressure is 0 at A. The velocity is 0 at A. So this whole left-hand side is 0. On the other side, we know what VA A squared over 2G is. We just found that. That's 1.61 feet. And we don't know what this term is. So that's what we're trying to find. That PA over gamma is minus 1.61 feet. So continuing up the pipe, let's apply the energy equation between points A and C. So again, on the left-hand side, all these terms are 0. On the right-hand side, this is the term we're trying to find. VC over 2 over G, that's 1.61 feet. And here, we have the HL term is not going to be 0. It's 0.1 feet per foot. So we have feet. We have 7 feet. So therefore, the PC over gamma is minus 2.31 feet. So continuing at point D, we again apply the Bernoulli's equation between points A and B. Left-hand side is 0. For the right-hand side, PD over gamma, that's what we're trying to find. This kinetic head loss velocity head loss here is going to be the same as it was before. Now the Z term is 8 feet. Uh, and there's no there's no turbine here, so that term is 0. At H of L, it's 8 feet plus 7 feet, so it's 15 feet. So remember, we're going from A all the way up to here, so that's why you get 15 feet and not just 8 feet. 15 feet times 0.1, so you calculate PD over gamma is minus 11.1 feet. So now finally we can draw the the grade lines. Here's the summary. So H of pump we calculated is 11.11 feet. The total head loss is P over gamma plus V squared over 2G plus Z. So based on the previous calculations, at A, you can see the head loss, the total head loss at A is 0. Then at C, it drops down by 0.7 feet. And then at D, it drops down another, it's minus 1.15 feet. And then at B, here it jumps up by 9.6 to 9.61 feet because, again, that's the value that we calculated. So it starts here at minus 11 feet, and we add H of the pump to it, which is 11.1. So minus 1.5 feet plus 11.1 feet gets you up to 9.61 feet. And here you can see the hydraulic grade line is just the values. It's the kinetic energy loss subtracted from the hydraulic the energy grade line at each point. So you can calculate those values. We did that on the previous slide. Just subtract from each one of these and get the difference between the energy grade line and the hydraulic grade line at each point. Okay, that's the end of this lecture. I'll see you in the next one.